Hello, my name is Nicole Gonzales. I'm a first-year grad student at the Lunar Reconnaissance Orbiter Camera Team at Arizona State University. I've been working on the Apollo 50th anniversary spatiotemporal maps. This presentation is specifically about Apollo 14. If you're interested in 11 and 12, we have done those at different conferences. This map follows astronauts Commander Alan Shepard, who many will remember as the first American in space, and his lunar module pilot Edward Mitchell, as they explore the moon on Apollo 14. These spatiotemporal maps recreate in map view what happened on the moon 50 years ago, minute by minute. This is what completed maps look like. On the left, we have EVA1, and on the right, we have EVA2. These are on the LROC website if you are interested in checking them out. So how do we create these spatiotemporal maps? First, we define events. Each event is a point that we map. An event is every time that an astronaut does one or more of the following. If they collect a sample, take a photo, whether that photo is a Hasselblad or close-up camera photo, if they deploy, retrieve, or otherwise interact with equipment, comment on local geology, or move to a new spot, whether that's to take a stereo photo, to change direction, or do something else of significance. Those are points that we have deemed important enough to map a point. Each of these events is mapped in QGIS in chronological order, which allows us to put all of the details back into context with each other. And in doing so, we can map more accurate coordinates for each point. We use the same basic process that the original Apollo science teams did. This was defined in the Apollo 11 preliminary science report. They started with the voice transcripts and the TV videos, added in the 16mm data acquisition camera videos, or DAC for short, and the Hasselblad photos. In order to make this process a bit easier, we developed a few web scraping Python scripts to help us out. The first converts the Apollo Lunar Surface Journal transcripts into a spreadsheet. This spreadsheet then becomes the foundation that we build off of. It's where we keep all of our temporal documentation. The second script collects the videos from the Apollo Lunar Surface Journal website. It automatically documents the starting and ending time of each clip, identifies any gaps between them, and then downloads all the clips. Those clips will then be manually reassembled with the audio into a full-length EVA video that we will use to map. And then, of course, we can get into the mapping. We always start with the most high-resolution LROC NAC images, in which we can see the trails of footprints and some of the equipment that was left behind on the moon. Then we add the transcripts and the panoramas to find the remaining equipment. Over on the left, you can see an example in a composite NAC image that shows where a few different pieces of equipment can be seen. And then we can get back to mapping those events that we took the time to define earlier. We always start with the transcript spreadsheets. Those are the ones that were created by the Python script a minute ago. Then we can build off those with the audio. We often use the tone of voice. If you can hear if they've got a strain in their voice, they're probably carrying or picking something up. Sometimes you can also hear an audible click when they lean forward. This is from their microphone bumping the hard plastic of their helmet. And then we can add to that with the TV and 16mm data acquisition camera footage. That allows us to map the small movements. And even when the astronauts themselves aren't within view of the video, sometimes you can still see their shadows. However, there are a few limits to that. The TV cameras were not yet mobile. They were still wired directly into the lunar module, as this mission did not yet have a rover. And the data acquisition camera, that's the film camera they carried with them, had the limitations of your standard film camera. It was limited by the frame rate and the length of that reel of film. While it was attached to the mobile equipment transporter, it was not actually all that useful because the MET bounced around a lot. You can actually see the MET here in this image on the left. This is the view from the TV camera during EVA2. Over here is the MET pulled by an astronaut, and you can see the beautiful tracks that it leaves behind as they walk around the lunar module there. So let's take a closer look at the MET. MET stands for Mobile Equipment Transporter. It was basically just a folded wheelbarrow that they could use to cart their tools and samples around on the lunar surface. It did have the data acquisition camera attached to the top, but unfortunately was rather bouncy when it moved around, and the data acquisition camera film had a tendency to get jammed and it wouldn't film their traverse across the surface, unfortunately. Now, an astronaut that's not pulling the MET tends to walk around like this. This is what Pete Conrad dubbed the lunar walk on Apollo 12, And you can see that as the astronauts walk around like this, they tend to kick up a lot of dust. And that dust kind of gives their tracks this extra dark, smudgy appearance, which you can see here on the right in this Hasselblad image. These are the tracks left behind by the lunar module pilot as they headed out towards the ALSEP on EVA-1. However, you don't see that extra dark smudginess over here on these tracks on the left. These were left behind by the commander as he pulled the Met across the surface. And the fact that you don't see that kicked up dust actually indicates that this astronaut was traveling a lot slower in order to not lose a lot of the equipment as the Met bounced around. Now, the other reason that they did not have TV footage is exemplified by this map. This is actually the same map that they carried with them on EVA-2 to navigate their way from the lunar module over here on the left, all the way up to the rim of Cone Crater on the right and back along this way. Unfortunately, what you can't see in this image actually is that this terrain is not very flat. But that topographic change can be seen in this NAC imagery. We can see the lunar module down here on the left and follow the little trail of footprints that they left over here on their way up to Cone Crater and back down around like that. But we can also see this little ridge here that's right next to the lunar module and would have prevented the TV camera at the lunar module from being able to see that trek up to Cone Crater and back. So when we don't have that video footage to rely on, we generally start reaching more for original Apollo documentation, whether that's like the EVA maps we were looking at, or the preliminary science report, or the mission report, or the technical debriefing document. It can even be things like the Hasselblad photos. Those are probably the best because they can show you the most detail. The close-up camera photos can also be quite useful. They were often taken rapid fire, and that can help you reconstruct the sequence of photos and where the astronaut most likely took them. The cuff checklists are also very important. The cuff checklists were worn on the astronaut's arm during the EVA, and it was their way of making sure they were in the right spot doing the right thing at the right time. They often had diagrams that looked like the one on the left here. This diagram was actually from the preliminary science report, but it's very similar to the ones found in the cuff checklist. And it will often show you little things like where they wanted to take photos, what sorts of samples they wanted to collect, where would they be with respect to the local craters, where to park the Met, and that sort of detail. Now, the Hasselblad photos are one of the most important pieces of data that we have, second only to the video footage. Not only can we figure out where the photographer was standing, where mobile equipment was placed, and where samples were collected, we can actually get so much more from it than just that. For example, since we know the sun angle on that day at that spot, we can figure out that from the shadows what direction the photographer was facing. And then when pairing that with something like the footprints, we can actually figure out what direction an astronaut was moving when they left those footprints. And that's because of something that we see up here in these GIFs. That's what Pete Conrad dubbed the lunar walk. It's kind of the skipping step that they use on all the missions to move quickly across the surface. And the way it works is that they would kind of land flat-footed and roll off the toe, which left these very specific imprints, which can actually help indicate what direction the astronaut was moving when they left those footprints. That being said, it doesn't always work. Perhaps next time it would be easier to have directional indicators in the actual tracks of the footprints themselves. And then our last step was to calculate the uncertainty. Starting with the temporal error on the left here, we used the Apollo Lunar Surface Journal transcript as our base reference point. We would take the very first and the very last comments that you can hear in the audio tracks and compare the length of time between those comments to the length of time between those same comments in the Apollo Lunar Surface Journal transcript. We found that over a 3-hour time period, our audio was actually 1 minute shorter than we anticipated it to be, which suggests that the audio was digitized at a faster rate than it was recorded. Then we get to our spatial error. We started with the NAC base maps to see if our base maps themselves were off from the actual coordinates or not. We used Wagner et al. 2017 as a reference point here, comparing the coordinates of the lunar module and the passive seismic experiment in both the Wagner et al. And our NAC base maps. And we found that we were off by 0.2 meters latitude and 0.35 meters longitude. Overall, less than 1 pixel in either direction. And then we moved on to the uncertainty in each individually mapped shapefile point. In instances where we have video, we should be within 1 meter radius of error. When we don't have video, that error increases to a radius of 5 meters for EVA-1 and 8 meters for EVA-2. This finished product includes individual shapefiles for each of the following categories. Astronaut events or movements were mapped per astronaut per EVA. We then went back through and connected those dots with the paths of travel for each astronaut for each EVA. We also have individual shapefiles for the samples, equipment, both stationary and mobile, the photos with individual shapefiles for the Hasselblad photos and the close-up camera photos, and any geology that they commented on but did not sample. There were also a few lessons learned during this Apollo mission that we thought important enough to reiterate here. The mobile equipment transporter, much like the hand tool carrier that preceded it, was rather cumbersome and actually slowed down the astronauts significantly. It caused Houston to even leave out a few important geology stations that they had planned to visit. And then we have the footprints. Unfortunately, the tracks left behind by the astronauts did not have any directional or personnel indicators in them, though that certainly would be a benefit next time. During this Apollo mission, they also collected a number of large rocks, which they didn't have sample bags large enough to put them in, which meant that many of these rocks were returned to Earth without individual numbers to identify them. And once again, I would like to reiterate that the finished product can be found on the LROC website. If you go to Featured Sites, Apollo Traverses Temporal Traverse. Thank you very much.